Welcome back. So we'll still be talking about DC circuits today. Quickly, last time we talked about the battery, the voltage difference across a terminal battery called terminal voltage, or has its own name, special name called electromotive force, epsilon, okay, or EMF. So just keep in mind, although it talks about force, but this is actually voltage, okay? All right, and then we talk about internal resistance of a battery, so that will actually reduce the terminal voltage by a little amount of I times R. We talk about the combination of resistors in series and in parallel. So when they are in series, the combination can be replaced by an equivalent resistor as a resistance of the summation of the resistance from each of resistor. When the resistors are in parallel, then inverse of equivalent resistance is equal to inverse of each one add up. Okay, and we talk about the procedures to calculate equivalent resistance for a complicated combination of in series and as well as in parallel from time to time. So today we'll be talking about, or actually last time we also talked about Kirchhoff's rules. In which you have more complicated combination as well as multiple sources in the circuit. So then there are two rules here, junction rule and loop rule, okay? But today we are going to move on, finishing up this chapter. So the next section here talks about electrical measurement instruments, okay? So there are several types of instruments that used to measure the current of the circuit, the voltage of the circuit, okay? So those are the two major ones. So let's take a look at them. So if you have a device that measures current, it's called an ammeter, which means ampere meter, right? In a sense. So, and if you have a device that measures voltage, it's called voltmeter, so voltage meter, okay? The ampere meter is used in the circuit, so then the current is flowing through the ammeter. So that means ammeter should be in series with the particular part of the circuit that you are interested in its current, and then its resistance should be as small as possible so that it does not actually interferes with the other elements in the circuit. All right. So in that sense, also then it's very easy to burn the ammeters if you have a short circuit. If you apply the voltage across the two terminals of ammeter directly, then you will generate a lot of current because the resistance is so small. So then you'll burn it out. Okay, so in a lab, it's very easy to burn the ammeter. All right. For a voltmeter, so you are measuring the voltage across a particular element. So for example, a resistor here. So in that case, so then this voltage meter is parallel to that resistor. Okay, so as the current goes into point C, junction C, it will split into two. So one's to IR, the other one's to this voltmeter. Okay, so if the resistance is smaller, then most of the current will go into that branch. If resistance is large, then very little current will go through that branch. Okay, so in this case, you want most of the current to still go through this element, right? So then that means your resistance for the voltmeter should be very large. Okay, so as large as possible, so that it's not disturbing the circuit itself. Okay. So in that sense, the voltmeter typically is not easy to burn as compared to the ammeter. Okay, and just keep in mind, so voltmeter was always going to be parallel to the particular element that you are interested in its voltage difference across the two terminals. An ohmmeter, which is also often used, okay, so to measure directly what will be the resistance of a particular element, okay. So the ohmmeter, actually, you actually have the two ends directly clipped to the resistor, okay? And oftentimes you'll see that the ohm meters, the reading will be in the logarithm scale, okay? So that means actually start from 0 and then 20 and then etc. So 10, 0, 10, 100, 1,000, etc. in the logarithm scale, okay? Now, if you have digital one, then you probably don't have the scale show up, okay? All right, so those are the three main devices you would use in the lab. So the next section is talk about the RC circuit. So sometimes, or most of the times for a circuit, you don't just have resistors or capacitors. We know they could already be being very complicated, right? But then a lot of times you will have both of them, okay? Resistor and capacitor at the same time in the circuit. So we'll take a look at actually simple RC circuits in this class only, okay? So that means let's just take a look on just one single resistor and a capacitor. Now, if you might have multiple resistors, but you can treat them as an equivalent resistor, right? So then you might also have a couple or maybe three capacitors, but they might be in series or in parallel or in combination. You can also treat those as just one single, okay? So if we know how to deal with just a single resistor and a capacitor, then we will be able to actually expand it into a little bit complicated scenarios. All right. So if you have RC circuit like this, a resistor and a capacitor combined in the circuits with the battery here. So this is called an RC circuit. So as you close the switch, then the charge will be moving from the positive terminal battery and then through this resistor and then deposit onto the upper plate of this capacitor. On the other hand, negative charge will be deposited on the lower plate here. So now you are storing charges on the capacitor, therefore store electrical energy onto the capacitor. Okay, and then later on you might retrieve the energy and then to use in for a part of the circuit. Okay, but let's take a look on the charging process. Okay, so once you have charged, so you have closed the switch, charge is moving around. Okay, so in that case, charge is moving through this resistor, so that will create a current. Okay, so then there's current actually in the circuit. Let's take a look on what would be this process in terms of time. Okay, so that means how slow or how fast will be the charge building up on the capacitor here. And after that, we can take a look on what will be the current going through this resistor. Okay, because if you know the charge amount over here, you do charge derivative charge over dt, that gives you current. All right. So I'm going to show you a derivation of this guy on the paper. So we have a circuit. A battery, a switch that is closed, and then a resistor R, and a capacitor C. Okay, something like that. So resistor, capacitor, and epsilon. Okay. So let's use a loop rule. So let's pick a loop. Okay. Loop. The current will go in this direction, right? And then goes through that. So if we start from this point, right, the direction of the current and loop here are in the same direction. So you got minus IR. Now across this guy. So capacitor behaves just like a battery in the circuit. Okay, so because you have positive and negative charges, so it stores energy, and then later on you can draw energy from that, the same as the battery. So if you go from positive to negative, so then that's minus, right? Minus the V across this guy. So then that's the Q over C, okay? And then encounter this guy, negative to positive, so plus epsilon equal to 0, okay? All right, now I, according to definition, is dq over dt, okay? So then minus dq over dt times R minus q over c plus epsilon equal to 0. Okay. So let's see. We can move this guy to the other side of the equation. So then on the left hand side, you have epsilon minus q over c equals to dq over dt times r. Okay. Here this is c epsilon minus q over c. Okay, on the one side equals to dq over dt and times r. So if you divide both sides by r, you get rid of that guy. So the r then, let's do this. Get rid of the r and then r comes here. Okay. Now differential equation here, right? So we want to put one variable on one side and then the other one on the other side. So dq is one of the variable, dt is another one. So, and there's a q here, so you want to move this term to be in the same side on this one, and then this guy can go to the other side. So then after that, you get dt over rc equals dq over c epsilon minus q. Okay. Then you can integrate from the initial point time t to final time t, and then on this guy, so initially you'll be having 0 and then final will be q. Okay, so this is 1 over RC. RC is a constant. Okay, so then this would be just T over RC from 0 to T. On this side, you have minus Q here. You have positive Q there. Okay, so you this will give you natural logarithm. Okay, so natural logarithm of C epsilon minus Q. Okay, and then because it's minus Q, so then it will be minus of that. Okay, from 0 to Q. Okay. And if this will be positive here, then you get positive. Okay. But if it's negative there, so you get negative. All right. So upper limits in minus lower limits in, right? And then upper limits in minus lower limits in. So then on the left hand side, you have T over RC minus 0 over RC. Okay, so it'll be 0. On this end, you have minus natural logarithm of C epsilon minus Q, right? And then minus of, right? So upper limits minus of C epsilon minus 0. Okay, in that case. So minus becomes positive. Okay, so then on the right hand side, you have T over RC. On the left hand side, you have on the right hand side, left hand side, you have T over RC. On the left hand side, right hand side, you have this becomes positive. So line of C epsilon minus, right, this guy, line of C epsilon minus Q. Okay. So line of A minus line of B, we know that it's line of C epsilon over C epsilon minus Q. Okay, equals T over RC. And here we call RC equal to tau. So then T over tau. Now we are looking for Q as a function of time T, right? So we will then do exponential. Okay. Let me see. Okay, yeah, that's fine. So, okay, so we got do exponential to both side equation. So exponential e to the t over RC or tau if you want equals to, then get rid of that C epsilon minus Q. Okay, now this guy is in the denominator, you can flip it, right? So that means inverse of this side. So that means inverse of that side. Inverse, you do inverse of both sides. Okay, so inverse of that becomes e to the minus t over tau, which is RC equal to C epsilon minus Q over epsilon. That was C epsilon. Okay. So then C epsilon can go to this side, both sides multiplied by C epsilon, e to the minus t over tau equals to C epsilon minus Q. Okay. So then Q goes to one side and then this guy to the other side. Okay. So Q then equals Q then equals to C epsilon minus C epsilon exponential of minus T over tau. Okay, so which is C epsilon of 1 minus e to the minus T over tau to be Q. That's a function of time T. And tau is equal to RC. Okay, so then this is what you get at the end. So let's go back to the slide. Okay. So this is then the result here. Okay. So the same as this shows here where tau equal to RC and tau is called the time constant of the RC circuit. C times epsilon will be the final charge on the capacitor Q because as T equal to infinity, that means you charge it for a long time. So then this guy becomes 0. Okay. So then the charge will be equal to that. All right. So here is a plot of Q over versus time T. And in terms of tau, like one time constant, after one time constant is about like 63% charge, two time constant close to 80% or a little bit over 80%, three times constant that would be close to 95 something, and then four times would be very close to 100%. Okay. So then typically after you have 4 time constants into the charging period, you can say this is almost charged, fully charged. Okay, you can just say charged. Okay. All right, take a look at the first example here. It says the switch on an RC circuit is closed at T equal to 0, given that epsilon equal to 6.0 volts, R equal to 92 ohms, and C equal to 28 microfarad. How much charge is on the capacitor at time T equal to 4.0 millisecond. Okay, so this is charging a capacitor, a RC circuit. So we are going to take this equation. Okay. So let's take a look on this. So the equation to use is this one. Okay. And it's asking you how much charge. Okay, so that means you are solving for that. Given T is equal to, so T is equal to 4.0 millisecond times 10 to the minus 3 seconds. Okay. R equals to 92 ohms, C equals to 28 micro 10 to the minus 6, the epsilon equal to 6.0. So we just plug in numbers, right? So Q then equals C times, C is 28 times 10 to the minus 6, V or epsilon 6.0 V, 1 minus exponential of minus T is 4.0 times 10 to the minus 3 seconds over tau, which is R times C. So tau is R times C. 92 ohms times 28 times 10 to the minus 6 farad. Okay. So that would be your charge. So everything together gives you 1.32 times 10 to the minus 8 coulomb or 132 microcoulomb. Okay, so either way. All right, so let's go back to the slide. For the current of the RC circuit, so then you do dq divided by dt. Okay, so quickly we can take a look on this derivation. So then you are doing derivative of this guy over dt. Okay, so this guy is like two terms. The first one will be like 1, and then second one will be the exponential function of t. So derivative of the first term, right, will be 0 because this is the constant. So then the result will be derivative of this guy. So then you have C epsilon times this minus of C epsilon times e to the minus t over tau, right? So then this becomes derivative of this guy becomes minus 1 over tau, which is minus 1 over C. 1 over RC, sorry, tau is R times C, okay? So then C and C cancel. So you have minus of, there's a minus and then a minus from minus 1 over tau, so then cancels. So at the end, you have epsilon then over r e to the exponential. Okay, so which is the what we have on the slide. Okay, so then the current, if you take a look on that in the slide, should be epsilon over r times e to the minus t over tau. So when t equal to 0, this thing is equal to 1. So that means the initial current should be equal to epsilon over r, and then decays down. Okay, again up to 4 times our time constant, then it's almost going to 0 in this case. Okay. If you look at the charge on the capacitor, okay, versus time t, we know that goes up similarly as the voltage will be like V is going to be equal to Q over C. So C is constant. So then it will be similar to this guy. Okay, so that's the voltage. On the other hand, so the current in the circuit will be like exponentially decay down. Okay, which means the current through the resistor is going to decay down. And the voltage then as a function of time on the resistor should be just the current times R. R is constant, so then it decay down like that as well, okay? All right, now let's take a look on discharging a battery or the discharging the capacitor. So discharging capacitor is similar to this circuit over here where you just remove the capacitor, right? And then connect it. So then the equation here to start with here, then you don't have this guy. Okay, so this guy then will be away, disappear in the equation. So then let's just have these two, we'll just have these two equal to 0. Okay, so that's what discharging a capacitor will give you. Okay, so then you'll start with the minus of IR minus Q over C equal to 0. Which is minus of VR minus V of C, okay? So minus minus becomes IR plus QC equal to 0. I again is dQ over dt plus times R plus Q over C equal to 0. Again, move this guy to the other side of the equation. So dQ over dt times R equals to minus Q over C. All right, let me make this larger so you can see it better. Okay, so this guy now goes to the other side. So you'll have dq over dt equals to minus q over rc. Okay, and then move this to the other side, move this guy over. You'll have dq over q equals to minus dt over rc, which again rc is equal to tau. Then you can integrate both sides of the equation. Okay, so integrating. Okay. All right. So this on this side will be line. Okay, line of Q. On this side will be just minus of T over tau. Okay. All right. So integration, so this is from 0 to T. Okay, and then this is from Q0 to Q. Okay. So then you actually not just having that, but minus, which means over or line of Q. So in this guy will be line of Q minus line of Q not equal to minus T over tau. Okay. So then line of Q over Q not equals to minus T over tau. Get rid of exponent. So then Q over Q0 equals to exponent of T over that. Q then equals to Q0 of e to the minus T over tau. Okay. And Q0 should be the charge of when the capacitor is fully charged. So that will be equal to C times epsilon. Okay, so then Q as a function of T is equal to C times epsilon e to the, so Q not equal to C times epsilon, okay, minus T over tau. So that's the result. We have, okay, as showing on the PowerPoint slide. And then go back to the slide. Then for the current will be derivative of Q over dt. Okay, so then that gives you Q times e to the minus t over tau. So minus t over tau will come down because here minus t over tau. So this is tau. Okay, so current then equals to this guy Q over RC. Okay, e to the minus t over tau, and Q is equal to epsilon O times C. So then this will be minus epsilon over R, okay, e to the minus t over tau. All right. So you can see that the charge on the capacitor will decay down exponentially. Its current or its voltage, so again, it's proportional to that, will also decay down. Now for the current on the capacitor, actually it goes up. Okay. So it starts from the initial one, or minus of the initial, and then goes up, but in this case, that means it decays to 0. Okay, so the minus will just mean the direction. The voltage across the resistor, okay, it also goes down as the current goes to 0, so then becomes 0. All right. Okay, let's take a look on this example. It says that figure below shows a simplified circuit for a photographic flash unit. This circuit consists of a 9.0 volts battery and 50.0 kilo ohm resistor, a 140 microfarad capacitor, a flash bulb, and two switches. Initially, the capacitor is uncharged and the switches are open. To charge the unit, switch S1 is closed, and to fire the flash, switch S2 is closed. How much time does it take to charge the capacitor to 5.0 volts? Okay, so this is 9 volts, and then it asks you, as this one is closed, how much time it takes it to charge this guy to 5.0 volts? All right. So this is still on charging a capacitor, okay? But it tells us now the final voltage. They ask us to find time t, okay? So we will still apply the equation we got previously. So then on the charging of capacitor, Qt is equal to C epsilon 1 minus e to the minus t over tau. Okay, so then v as a function of t should be equal to q over c, which gives you epsilon 1 minus e to the minus t over tau. Okay, so this will be v. So it tells you 5.0 volts, and then initially that's 9, or for the battery volt, that's 9. 1 minus e to the minus t over tau. Tau is R times C, so R is 50 kilo ohms times C as 140 microfarad. Okay, then you can solve for T. Okay, so here this multiplied by that gives you actually 7 exactly. So then you divide both sides, so by 9, so 9 over 5 equals to 1 minus e to the minus t over 7. Okay. You'll move this guy to the left, move this to the right. So then e to the minus t over 7 equals to 1 minus 5 over 9. This gives you 4 over 9. Okay. So then natural logarithm of e to the minus t over 7 equals to natural logarithm of 9 over 4. So on this side will be minus 7 t over 7 equal to natural logarithm of that. Okay, so you solve for t, then t will be 5.67 seconds. Okay, so it takes 5.67 to charge the capacitor to 5.0 volts. All right. Oops. Okay. Now quickly on the last section, talk about household wiring and electrical safety. So if electricity are not handled properly, so there are two main hazards. One is called thermal hazardous, the other one is called shock hazardous. Okay, so the thermal one is that where excessive electric power causes undesired thermal effect, so then catching fire, okay, in the wall of a household. Shock hazards is when the electric current pass through the body of a person, which then have serious consequences. Okay. So take a look on the first one, thermal hazardous. Okay. So for example, if you have wire that is warmed out, so typically if there's a wire for the appliance, so in that case, there are two wires insulated by dielectric materials, insulators. Okay, so for if it's too old, then this might be the insulation might be warm out. So then the two wires will come to direct contact. So then the electricity will go through that part because that part will then have very small resistance than the main appliance. Okay. So for example, if that part only have 0.1 ohms, then 120 volts of the um, electricity applied to through that one, it produces a power of 144 kilowatts, which then can increase the temperature of this part very significantly, which might result in the ignition of the part of the material. Okay, so then causing fire. So one way to prevent that is by using fuse, okay, or circuit breaker. So there are two ways. Okay, so for the fuse is one part of the circuit that has this fuse that has a metal inside which has lower melting point. So if a large current going through that, then it heats up this part and will melt the metal here, then cuts off the electricity. Another way is to have a circuit breaker where there's a needle here in the circuit that is made up by metal strips. So then as temperature goes up, if there's a large current going through, so expansion of the two metals are disproportional to each other. So then we'll make this needle bend to one side. So in this side, and then that follows into this stick there, then cuts off this circuit. Okay. Short hazardous. All right. I hope you guys didn't have any experience of that, but I remember I was very, very little. This is one of my earliest memories in my childhood that I remember I put a push pin, a metal push pin that has like this button shape of um the one end, and then the other end is like needle. So I put that into the power outlet when I was so young. And then I was shocked by the electricity, but luckily, I think I was on the second floor of the house, and then I probably was wearing shoes. So it was the initial contact was very unpleasant, but I wasn't like on the ground. So if in this case, if you are grounded and then not wearing proper insulated shoes, the current will go through your body, and that would be very dangerous. Okay. So if current is small, very small, that's okay, but it's very easy to get current that is at the threshold of our sensation. So then you can feel that, okay, and then if it goes up, then to a certain point, the current goes through your body is too big, then you actually cannot control your body. The nerve system will no longer work same, you cannot let go, so then it's very fatal. Okay. All right, so that's it for this chapter, and then we'll stop here. Okay, I will see you guys next time. Bye.